All right. Oh, my mic is a lot louder today. Cool. Welcome back. Welcome back, everybody, to CE 374 Use Urban Stormwater. If I could get your attention so we can go ahead and get started. I got a couple of announcements. Well, actually, just one announcement, really. Homework 3 is due next Friday. So be aware of that deadline. And has anyone started homework 3 yet? Okay, good. Please let me know if you run into any technical problems by this week, please, because it will be hard to catch up if you have technical problems next week. So if you have any problems at all installing or running ArcGIS on your computer, please let me know this week, preferably by today. Right. Are there any questions on general questions about homework 3 that could benefit the class? Yes.
Trying to submit the map.
Mhm.
Okay, if it's just a screenshot.
Yes, you can take so for anything asking for a map, you can simply take a screenshot of the layout view. Yes, good question. Thank you. Any other general questions about homework 3? Yes.
For ArcGIS, you have typed out notes for HMS.
I don't have a set of typed out notes, but the recordings are up on under the Pages tab in Canvas. So that's the primary resources that I would have. Yes. Cool. Any other questions on homework 3? Okay, so just as a reminder, for your homework submissions, you are encouraged to discuss the homework problems together and you can work together, but when you go to actually submit your assignments, those are expected to be your own work. So this isn't a group assignment, so you can't simply all do the same map and then submit it. Okay, you all have to submit your own maps, okay? So just be aware of that rule, okay? Great. Are there any other questions on course logistics or anything else before I move on? Oh, did you have a question? No, okay. Cool. All right. So with that, let's go ahead and move on. So we're gonna kind of take a new tack starting today. So previously in the course, we focused on kind of the theory behind how water moves and behaves in urban environments. And we had 2 major modules. By the way, there's no need for computers today. So today is a regular kind of class session day. So previously we focused on the theory essentially of how water moves through the urban water cycle. And we covered 2 main modules. The first was our module on hydraulics or open channel flow. And our second was our module on hydrology. Okay, so first we kind of did a review of hydraulics, open channel flow. What are some concepts? What are some key concepts from our study of hydraulics in urban stormwater systems? What are some equations or key concepts that you remember from hydraulics? Yes.
The St. Bernard equation.
Yeah, St. Bernard equations. That's kind of the most fundamental way of representing flow in open channels. So very good. What are some other concepts from hydraulics? What are some other concepts or equations you remember? Energy equation, very good. Okay, what other concepts or equations did you apply perhaps in your homework? Manning's equation, very good. Okay. Great. And any other concepts that you remember from our first part of the course? I want your top 10 concepts. Well, I'm not actually going to do 10, but any other crucial concepts? There's one more I can kind of think of. Yeah, so continuity equation. So that would be, I'll put that as part of, well, I'll just write continuity. But we also talked about sub, super, and critical flow, right? So these kind of give us the theoretical basis for understanding how water moves in our stormwater infrastructure. The other module that we covered was stormwater hydrology. So what are kind of some key concepts in stormwater hydrology that you remember? Perhaps more broadly, what were we trying to do in studying urban stormwater hydrology? What was the goal here? Yes. Right. So we wanted to find infiltration and runoff amounts. Okay, and why would we need to know that? Why would we need to know infiltration and runoff amounts? Yes. Yeah, we can model sheet flow. So after you compute infiltration and runoff, you can model the sheet flow across a land surface. Kind of more broadly, what were we doing when we looked into the hydrology of urban drainage systems? What was kind of our end goal? Yeah, so we want to be able to understand what our contributing area is for a given stormwater fixture. Kind of more broadly, though, we wanted to understand how much water our stormwater infrastructure needs to handle, right? So in the hydrology part of the course, we were concerned with estimating the amount of flow that our stormwater infrastructure is going to need to accommodate. So for instance, how much rainfall can we expect in a given area? How much of that rainfall actually becomes runoff? And how does that runoff route over the landscape? So what are the time dynamics of that runoff? How fast does the peak occur? And what is the peak discharge that we need to expect? Okay, so our hydrology section of the course was essentially concerned with understanding how much water is our infrastructure going to need to accommodate. Okay, so in those first two sections of the course, we were interested in kind of characterizing, the fundamental behavior of how water moves in our urban stormwater systems and how much water we need to account for when we're designing our stormwater systems. From now on in the class, we will be dealing with the design of stormwater infrastructure. Okay, so we're going to take the knowledge that we learned from the first part of the course, and we're going to apply it to understand how to size and design stormwater fixtures such as, the things that you see around you all the time, gutters, curb inlets, sewer pipes, culverts, detention and retention ponds, channels, which you'll be looking at in particular for your course project, and then GI or green infrastructure. Okay, so we're going to be using all of the concepts we learned from the first part of the course. We're going to be applying them to understand how to design these elements that make up so much of our urban infrastructure. Okay, and that's what we'll be looking at for the remainder of the course, both in class and in your course project. Okay, are there any questions conceptually before we move on? Yes. Yes, I will do that. Yeah, I just haven't had time, so I'll do it next week, and I will hand out awards for each category. Okay, so yes, I'm glad you remembered that. It's still coming. Yes. GI stands for green infrastructure. Okay, does anyone remember what green infrastructure is? Yeah.
Just like we use plans and other forms to create drainage,
Yeah. So what is green infrastructure primarily used to do, or what is it meant to achieve?
Not like floods, but like conditions.
Right. So that is one purpose of green infrastructure. Does anyone else remember what else green infrastructure is designed to achieve? Yeah. So probably the primary reason for green infrastructure is to improve water quality and remove contaminants from impervious areas like streets, parking lots, sidewalks. So Yeah, we'll be looking a little bit at green infrastructure in the course project and towards the end of the course. Great. Any other questions conceptually before we move on? Okay. And in the next couple of weeks, I will start to slowly introduce the course project. To get started in earnest on the course project, you will need to have knowledge of heckgrass first. So we'll need to cover that before we can really get started on the course project, but I will start to kind of ease into the course project as we move forward. Okay, great. Okay, so the first type of stormwater infrastructure we're going to design is these first two, so gutters and curb inlets. So this kind of falls under the umbrella of street and highway drainage. So a lot of you may end up doing this as practicing civil engineers. Quickly, before I get started on that, though, I just want to introduce you to this resource. So under pages, there will be a page on HEC 22 Urban Drainage Design Manual. So this is the Hydrologic Engineering Center Urban Drainage Design Manual. This contains a lot of the equations as well as the design criteria for a lot of the urban drainage infrastructure we'll be designing in class. And this will be a good resource for your course project. So I just want to make you aware of this. It contains pretty extensive documentation on how to design everything from gutters to inlets to ponds to pretty much anything you can think of related to stormwater infrastructure. So this will be a good resource for your course projects. Okay, and many of the equations that I'll be introducing in class essentially come from this drainage design document. Okay, so first, let's talk about our first element of stormwater infrastructure design, which is gutters and curb inlets. Okay, so first, before I get started in earnest, I'm just going to show you a couple pictures and get you familiar with curbs and gutters. Okay, so first, I just want to introduce a little terminology to be clear here. So we're interested in designing both curbs, curb inlets in particular, and gutters. So the curb inlet actually refers to the opening in the curb into which water flows and which connects to the stormwater pipe system underground. The gutter refers to essentially just the section of the street that forms a channel along the side through which water is conveyed into the nearest curb inlet. Okay, so when I'm talking about curbs and gutters, curb inlets refer to these openings, gutters refer to the actual channel. Kind of more broadly, what are we interested in when we're designing curb inlets and gutters? What are we trying to do kind of in broad terms? Yes. Right, so we're trying to keep water off the roadway. And each of these components serves its own purpose, which we'll talk about in keeping water off the roadways, and each has its own design criteria with respect to that goal. Okay, so we have curb inlets and gutters. Just a little bit more terminology. So the gutter refers to the actual channel section. So that's that flat horizontal part, whereas the curb refers to the curb of the sidewalk. Okay, so I just want to show you a couple pictures of curbs being constructed. So this is an image of the manual framing of the curbs. So typically they're framed with these kind of wooden frames like this, and then they're often laid by a machine. So this is an image of a gutter being laid by machinery. And here's just a picture of a completed gutter section. So this is typically done after the road base is laid, but before the road is paved. Okay, so those are just some images of curbs and gutters. Okay, so now that we kind of have some background, let's talk a little bit about what we're interested in for curb and gutter design. So as you mentioned, our primary goal in designing curbs and gutters is to keep water off the roadways. So this is the primary goal of curbs and gutters. We're going to be talking about two subjects in these next two lectures: curbs and gutters. Okay, so we're going to be talking about two primary subjects. First, we are going to focus on the design of the gutters. So this is the portion that acts as a channel along which water will be conveyed along the streets. So first, we're going to focus on the gutters. And the objective, our objective in designing the gutters will be to limit the spread. That's right, we will limit the spread of water on the roadway. Okay, and note that this is a technical term, spread, which we'll be talking about a little bit later. Okay, in the next class on Thursday, we'll be talking about the other component, which is curb inlets. Okay, so next time we'll focus on curb inlets. So these are those openings in the curb. And we are going to design them to limit the discharge in the gutter. Okay, so essentially in designing the gutters, we're going to be trying to limit the spread of the water across the roadway. In the design of the curb inlets, we're going to figure out how to size and place them in order to intercept water to reduce the amount of discharge in the gutter and thus reduce the spread. Okay, so those are going to be our primary design objectives. Okay, so let's talk a little bit about this first component, our gutter design. Actually, more broadly, I'm just going to talk about design of curbs and gutters together. So in designing curbs and gutters, there are a couple issues. So we're going to be talking about three main types of issues. We're going to talk about safety issues. We're going to talk about hydraulic issues, and we're going to talk about cost issues associated with the design of both curbs and gutters. So let's think a bit about what safety issues there are surrounding curb and gutter design, curb inlet and gutter design. So what are some safety issues you can think of surrounding the design of curbs and gutters that need to be met? What are some safety issues? Yes. Okay, yeah, so if it's, so you're talking about the curb itself? Okay, so you can't make curb too tall. Yes.
Hitting your car with it.
Okay, so you can, is this from personal experience or? Oh gosh, okay. So you may. Right, okay, so hitting the curb with your car can damage it. Let's think a little bit about kind of in general, what's the purpose of building these curbs and gutter systems in the first place in terms of safety? So why do we want these systems in place in the first place? Yeah, so it can prevent roadway flooding. Okay, it can prevent flooding of the roadway. So kind of more generally, so what are some issues with having too much water on the roadway? Yes. Hydroplaning, exactly. So a thin layer of water on the surface of the roadway can cause hydroplaning. Okay, which can potentially cause you to lose control of your vehicle. So you especially don't want this on larger roads. Okay, you don't want water too far along on the roadway such that hydroplaning occurs. Kind of more generally, let me just write this down. Water on the roadway has several negative effects on driving. So it affects steering. It affects braking, so it increases the skid distance. And it also affects visibility. Okay, so if there's too much water on the roadway, that can obscure lane markers, for instance. It can also potentially get kicked up by vehicles, which can reduce the visibility of the tailing vehicle. So it's important to make sure that there's not water on the roadway, even if it's just a little bit. Okay, and you know, as you mentioned, also you also want to reduce flooding, because that can be potentially lethal if you're driving along a roadway that's flooding. Okay, so there's other safety issues. Can anyone else think of more safety issues? Yes.
Interesting, but like if you have an asphalt pavement and there's like lots of water.
Exactly. So too much water can create potholes. You generally want your roadways to stay dry. Yes.
Water takes up like heavy metals and like other toxins off the road.
Yeah, it can. Yeah, so I would have to think about whether curbs and gutters can
I don't know if they help
reduce
in
that.
everything,
Yeah.
but it's like way-
Yeah, so that is a safety issue associated with water on roadways for sure. I'm not sure if curbs and gutters can affect it, although green infrastructure along the side of the roadway can potentially treat some of those heavy metals and other contaminants, which we'll be talking about later on in the course. Okay, are there any other ideas for safety issues related to curb and gutter design? Maybe in respect to the design of the curbs and gutters themselves. Can anyone think of any safety issues associated with their design?
So, like if the curb inlet is too big, like a hole, I would imagine it's pretty easy for a small child to fall into it.
Yes, that is true. Yeah, so that's one of the ones on my list, and it's an important design consideration. So large curb inlets are hazardous to small children. Okay, so you don't want the curb inlets to be too big. Okay, there's a couple other I can think of. Oh, yes.
Like accessibility for like intersections, I guess.
Right.
Slopes so you can get to the street.
Right, so accessibility is important at crosswalks and other intersections. Are there any other safety issues you can think of with respect to the design of the curbs and gutters that we're going to need to think about in terms of our design? Yes. Okay, so I'll put that back here. Can't make curb too tall, and we also can't make it too small. Okay, there's one more I can think of. And it has to do with the types of traffic moving along the road. So why might we not want to make the gutters too steep? Oh, yes. Right, yeah. So for bicycles, steep gutter slopes, so steep lateral slopes can be hazardous. And also graded curb inlets can also be hazardous. And that about covers all the safety issues I can think of. Are there any other safety issues you can think of that will be important to consider? Any more? Okay. those are the main ones we're gonna have to think about in terms of design, and those are the ones that are often included in drainage manuals like the Austin Drainage Criteria Manual. Okay, so we have safety issues. We also have hydraulic issues. So this concerns, essentially the depth and discharge in our gutter and how much we want. So can anyone think of any hydraulic issues that we're going to need to consider, or trade-offs that we're going to need to consider in our design of gutters, just based on your knowledge of open channel flow? Anyone think of any hydraulic issues that we're going to need to think about? This is kind of a vague question, but yes.
In like if it's slowly steep enough, like you have to correct the slope so that the water can get.
Right. So when you say slope, you mean the lateral slope? Yeah.
Sometimes there are low areas where water collects, but there's no gutter.
Right.
So uphill and it's kind of trapped in the flow.
Great. So that would be called, so there's a specific type of curb inlet that's used to correct that called a sump or sag inlet. So we'll have to think about any sags in the local drainage gradient. So I'll give you kind of, I saw another hand. Was there another hand? Did you have a idea?
Just like in general, like the drainage system has to be like at a slope going down. You know what I mean, like the actual channel.
Yeah, so the longitudinal slope?
Yeah.
Okay, so so that's actually on my list here. So we need the longitudinal slope to be sufficiently steep. For one thing to, achieve enough discharge, but also you need to achieve sufficient steepness to achieve what's called scouring velocities. So this is actually regulated into gutter and drainage design. So I'll say both for discharge as well as for achieving scouring velocities. Does anyone know what this is?
Stop stuff from being stuck.
Yeah, so this is to prevent accumulation of debris in the gutter. So you want your water flowing fast enough that it picks up that debris and moves it. You don't want too much debris accumulating. So Austin DCM actually mandates a slope of at least 0.004 in the Austin Drainage Criteria Manual. So your longitudinal slope has to be at least this steep. Okay. So another hydraulic issue that I will this is kind of a trade-off. So flow is you'll generally get more flow in steeper angled gutters. Okay, so when your lateral slope of your gutter is steeper, you'll get a larger discharge for a given spread. So flow is generally better. You'll get more flow in steeper angled gutters. But again, this can cause safety concerns for bikes. So often what we will do, as you'll see later on in class, is we will have a gutter with two different slopes, one with a steeper slope towards the curb and a shallower slope towards the street. Okay, and that's called a composite gutter. Okay, are there any other hydraulic issues you can think of? Yes.
Material, like you can only do, you can't really do like
cast iron or, like, you can only really do.
Yeah,
Concrete.
materials are limited. Okay, any other concerns with the hydraulics that you can think of? Yes,
Like, it has to be accessible.
okay. Has to be accessible for maintenance reasons. And there's one more that I want to just make you aware of here. I'll just leave this up for a second. Oh, yes.
Be flexible.
Yes, so we'll talk about that a little bit more when we get to storm sewers. So right here, we're just going to be concerned with the gutters and the curb inlets, but the curb inlets will feed into those pipes that go underground. Yes, so that is something we will have to consider later on. Okay. So one more hydraulic issue I want to make you aware of. We need to capture all the flow before an intersection. Okay, so we can't have flow from a street pouring into an intersection downstream. We need to make sure all of that flow for a given design storm is captured. In the Austin DCM, that's usually for a 25-year storm event. Okay, so we need to capture all the flow before we reach an intersection. Okay, great. Are there any other issues you can think of? Yes.
Geometry.
So that's what we'll be designing. And the rest of today, we're going to be designing the geometry of the gutter. Okay. Finally, as with everything else in civil engineering, there are a number of cost issues. Okay, so these will also affect our ultimate design. And primarily the cost issue that we have to think about is that curb inlets, the actual openings, are relatively expensive. Okay, so curb inlets are expensive. Okay, and we want to limit the number required. Okay. So in general, fewer longer inlets are cheaper. So if you have, if you have longer inlets and you have fewer of them, that's cheaper to construct, but they're less hydraulically efficient. And we'll be thinking about this primarily when we get to curb inlet design on Thursday. But it's one of the primary costs we have to think about. Okay. Are there any questions? Any questions? Any other ideas of cost considerations that we're going to need to think about? Any ideas for cost considerations? Materials. So what kind of materials do we want? Low cost. Hydraulically, what kind of materials do we want? Impervious. What do we want to achieve with our gutters? Yeah, we want the flow to move fast. We want to produce a lot of discharge. So that means we want it to be low friction. Okay, so low friction is more hydraulically efficient. Okay. Great. Okay, so let's talk a bit about what our requirements are for constructing curbs, gutters, and curb inlets. Let's focus first today on just the gutters themselves. So let's think about requirements for gutter design. So for gutter design, we are interested in, I'll just say it first. So we're interested in designing gutters to maintain a specified clear width. Okay, and I'll draw what this is in a second. But essentially, we want to maintain a certain width of the roadway that does not have water on it. Okay, do you have a question or no? Okay. Okay, so we're interested in designing gutters to maintain a specified clear width. So let me go ahead and draw a picture here. Let's say we have a roadway. I'm gonna draw it like, draw it a little further down. So we have a roadway. So this is looking longitudinally down the roadway. I'm gonna try to make them even on both sides. There we go. Okay, and we might have a gutter coming up like this. And there's the sidewalk here. I'll draw the same thing on the other side here. Okay, so this is a roadway. Let's say that this is a residential collector. Oops. Okay, so this is a residential collector. It has a kind of a regulated width. So let's go ahead and draw the dimensions on here. We have a residential collector. It is 24 feet wide with 12 feet on each side. Actually, let me draw this one in green here. So the width of the roadway is 24 feet and we have 12 feet on each side. And when water falls into our roadway, it'll kind of collect along the sides here. So you might get something like this, you get water coming out onto the road. Okay, so we want to maintain a specified clear width. For a residential collector in Austin, the mandated clear width is 12 feet. Okay, so that means that from here to here, this needs to be 12 feet long, which means that the water can have a spread of 6 feet on each side. Okay, so this here, this is called the clear width. So it is essentially the part of the road that doesn't have water on it. And this here is called the spread. Okay, so not necessarily. So I'm going to show you for Austin. I'll just give you a second to draw this down, but it's regulated by the Austin Drainage Criteria Manual. Okay, and different types of roads have different specified clear widths that are allowed. For some of them, it's that only the entire road needs to have a certain clear width, and then for other types of roads, each lane, so each direction has to have a certain clear width. For a residential collector, it's just for the entire road. Okay, so I will go ahead and show you from the Austin DCM. Did anyone still need time to write that down? Okay, so here is the section of the Austin DCM on street flow, so street and highway drainage. And if you want to find the specified clear width It's underneath section 3 here. If you go down to minimum clear widths for roadway design when gutter is flowing full, you'll see that for a residential collector, the minimum clear width is 12 feet. For a local road, there is no minimum clear width, so potentially the entire road could be inundated. And then for larger roads, you'll have generally more restrictive criteria. So you'll need to have 24 feet in each direction for a arterial 4-lane road. Okay, so I will be coming back to this table a little later on when we do an example, but you can always find, the design specifications for different roads by looking in your local drainage criteria manual. Okay. Are there any questions conceptually on what we're trying to do with gutter design? No? Okay, so just again, to summarize, we're interested in designing the gutter to maintain a specified clear width. Okay, we want to limit the spread of the water on the roadway. So let me talk about the two main types of gutters that we'll be looking at. So there's two main types of gutters. The first is a simple gutter. And the second is a composite gutter. Okay, and a simple gutter is, kind of what it sounds like. It's a relatively simple kind of gutter. It is essentially just a triangle, and we're going to treat it as a right triangle here. And the water collects in this gutter like so. Okay, so we have essentially the street is over on this side, and the curb is here. Okay, so this is a simple gutter. We're going to be looking at this in the first part of class today. In the second part of class, we will look at composite gutters. So I'm going to draw it kind of facing the other direction here. But essentially, a composite gutter is able to achieve kind of a compromise between safety and hydraulic needs by having a gutter with two different slopes. So towards the curb, it will have a steeper slope, and then towards the street, it'll have a shallower slope like that. Okay, and this, like I said, kind of achieves a compromise between safety for cyclists and hydraulic efficiency for better drainage. Okay, so on this side is the street. Okay, cool. Are there any questions on different types of gutters before I move on? Cool. Okay, so what we're going to need for our gutter design is essentially a way of relating the expected discharge in the gutter to the spread across the roadway. So that's what we're going to be looking at for this next part. How to relate the discharge in a gutter to the spread. Does anyone have any ideas for how we might go about doing this based on the material we've covered in class so far? How can we relate the discharge in the gutter to the spread? Right. This is essentially an open channel flow problem, right? If we think about the system just being at steady state, how might we go about relating the discharge in the gutter to the geometry of flow, essentially? Did I hear Manning's equation? Yeah, so like most things in urban stormwater design, we're going to be using Manning's equation for this problem. Okay, it's going to be a little bit more sophisticated than just applying Manning's equation directly. But I'm going to show you a method for how we can relate the discharge in the gutter to the spread. And this is what you're going to be using for the purposes of design. So we're just going to be looking at a simple gutter first. Let's go ahead and draw our simple gutter. I will use the line tool instead. All right, so I'll draw it, and I'm going to draw some dimensions on it this time. Okay, so we have our simple gutter. Let's draw some dimensions. We will call the depth of the water at the curb D. Okay, so we'll call this D. We'll say that the angle with the horizontal is theta. And we'll call this distance here TW. So this is the width of the spread. Okay, and this will be equal to, if you just use trigonometry, this is equal to D divided by the tangent of theta. Okay. So to figure out the discharge for a given spread, we're going to look at an infinitesimal element of flow along this gutter section. Okay, so it's divided into a triangular portion and a rectangular portion. Okay, we're going to call the height of this rectangular portion H. We're going to call the height of this triangular portion DH. We're going to call the width of this rectangular portion DX. Okay, and we're going to look at the discharge in this infinitesimal portion here. So the discharge within this tiny infinitesimal element is dq, and it's going to be equal to u, which is the velocity in that element, times a, which is the cross-sectional area inside that element. Okay, what is an expression for a in terms of the variables we have labeled here? So this is equal to u times, sorry? What's the area of just the rectangular portion first? Yeah, so it'll be h times dx. And what about the triangular portion? What's the area of the triangular portion? Yeah, so it'll be plus 1/2 base times height, which is 1/2 dx dh. Okay, so we can simplify this. U times dx times h plus 1/2 dh. Okay, now are there any ideas of how we can get this velocity? How can we get the velocity of this flow in an open channel? What equation do we have that relates the velocity to the flow for uniform flow conditions? So someone said it earlier. We can use Manning's equation to compute this velocity, right? So Manning's equation can both be used to compute the discharge, but in its original form, it was relating the velocity of flow to the geometry of flow, essentially. Okay, so we can find an expression for u using Manning's equation. So from Manning's equation, we have that the velocity is equal to phi over n times the hydraulic radius to the 2/3 power times the longitudinal slope to the 1/2 power. Okay, and we can rewrite this as phi over n. What's the hydraulic radius again? Area over what? Wetted perimeter. Very good. Okay, so we have that quantity times the longitudinal slope to the 1/2 power. Okay, and we've already got an expression for the cross-sectional area. What about for the wetted perimeter? Let's rewrite this out. So we have u is equal to phi over n times, we'll just plug in our formula for the area here. So we have h plus 1/2 dh for our area. Sorry, both of these are multiplied by dx. So we have dx h plus 1/2 dx dh on the top. What's an expression for the wetted perimeter? Just from geometry here. So first of all, what is the wetted perimeter on this diagram for this infinitesimal element? Sorry? So on this diagram, it'll be this right here, right? Which is just the hypotenuse of this triangle. Okay, so we can get the wetted perimeter as square root of what? Yeah. Yeah, dx squared plus dh squared. Okay, and this is all to the 2/3 power times bottom slope to the 1/2 power. Okay, so we can rearrange this to simplify it. First, I'm going to define a new slope. So let's define the lateral slope, which is this slope here, as s sub x. And s sub x will be equal to dh divided by dx. Okay, so it's this lateral slope here. And it's also equal to d divided by our spread tw. Okay, so it's just this lateral slope here. Okay, and so note that because sx is equal to dh dx, we also have that this expression here, dh squared is equal to dx squared times sx squared. Okay, and that just comes from this relation here. So we can go and substitute that in here. We'll have that u is equal to phi over n times dx times h plus 1/2 dx dh over, and if we substitute this in, we have that dx squared plus dh squared is equal to square root of dx squared plus dx squared sx squared. We can factor out the dx squared, and so what we end up with is dx times square root of 1 plus sx squared. And so we'll put that in on the bottom. We have dx times 1 plus sx squared. Take all of this to the 2/3 times the bottom slope to the 1/2 power. Okay, and we are almost there. Okay, so what I'm going to do is for this bottom part here, how does the lateral slope sx relate to 1? Essentially, what we can do is, if we recognize that the lateral slope sx is much, much less than 1, then this expression here on the bottom essentially just becomes square root of 1. Okay, so we're going to recognize that sx is much, much less than 1. Okay, so we can simplify our expression for u. U is approximately equal to phi over n times h plus dh over 2, all to the 2/3 power, times the bottom slope to the 1/2 power. So essentially, we've just assumed that the lateral slope is very small compared to 1. Okay. Furthermore, we're going to assume that dh is much smaller than h. So h plus dh over 2 to the 5/3 power is approximately equal to h to the 5/3 power. Okay. So essentially dh is much smaller than h. And with that, we get the following expression for dq. dq is equal to phi over n times h to the 5/3 times sx, dh divided by the lateral slope times the longitudinal slope to the 1/2 power. Okay, and we can integrate this because we have a dh on the right-hand side, a dq on the left-hand side. If we integrate this across the length of the gutter, what we end up with is the following equation. Okay, so we're going to integrate across the gutter. We get the following expression for q. If we integrate that, we get k over n times the longitudinal slope to the 1/2 power divided by the lateral slope times d to the 8/3. So essentially that 8/3 comes from this h to the 5/3. When you apply the power rule, that becomes 5/3 plus 3/3 is 8/3. Okay, I'm not going to do the full integration here, but you end up with this expression that relates the depth in the gutter with the discharge. Okay, so we're almost there. We're almost there. The last thing we have to do is recognize that there's a relationship between the depth in the gutter and the spread. Okay, so we remember that we have that the spread, TW, which is what we're interested in, is equal to the depth divided by the lateral slope, SX. Okay, and with that, we can essentially plug in this expression for D. So we substitute this expression in, so we can remove D. And what we end up with is the following equation. This will be our final equation. What we end up with is what's called Izzard's equation. So this is an important one. This is equal to Q is equal to K over N. So sorry, I haven't explained what this K is yet, but I will in a second. Is equal to K over N times the longitudinal slope to the 1/2 power times the lateral slope to the 5/3 power times the spread to the 8/3 power. Okay. K is a constant that comes from the integration, and it incorporates that phi parameter into it as well. So K is a constant, is equal to 0.56 for US units. And K is equal to 0.375 for SI units. Okay. But this gives us a way of relating the discharge in the gutter, so the discharge for an expected storm event of a given recurrence interval. It gives us a way of relating that discharge to the expected spread in the gutter, which is what we're going to be using for the purposes of design. Okay, so I'm going to give you an example problem to work on to apply this. Okay, let's do a little design here. Okay, so I want you to consider a simple gutter. Consider a simple gutter. We're going to have the following parameters. So the cross slope or lateral slope SX will be equal to 0.02. The longitudinal slope S naught is going to equal 0.025. Our Manning's roughness is going to be equal to 0.013. And the discharge, let's just say it's for a 25-year storm event, is going to be equal to 1 cubic foot per second. Okay, so what I want you to do is, using these parameters and using Izzard's equation, I want you to determine the spread. I want you to determine the spread. And let's say that next, the gutter is located on a residential collector. That is 24 feet wide. So this includes both lanes. And the required minimum clear width is 12 feet. So I want you to find out, does the gutter meet the minimum clear width for this discharge rate? And I'll give you about 5 to 10 minutes to work on this problem. And I will come around and check on you as you do so. All right, so in the interest of time, I'm going to move on. Okay, first, for the spread, what is the spread expected for this discharge rate in this gutter? Right, TW is equal to 5.6. So you can get this simply by rearranging the equation, Izzard's equation, so that we have Qn in the numerator. We have K times the lateral slope in the denominator to the 5/3 power times the longitudinal slope to the 1/2 power, all to the 3/8. If you compute this, you should get about 5.6 feet. Okay, and I think everyone got that one, right? Okay, second, does it meet the clear width requirement or not? Yes. Okay, so yes, clear width requirement is met. Why is that? Well, we can see it geometrically. Just if we look at the roadway. Okay, we have that the roadway is 24 feet. We need a clear, we need a requirement of 12, essentially 12 feet. Okay, so essentially the allowable spread is 6 feet. Allowable spread is 6 feet. We have a clear width requirement of 12 feet. And because 5.6 feet is less than 6 feet, we meet the clear width requirement. Okay, very good. Okay, are there any questions on simple gutters before we move on? Okay, I think I have just enough time to introduce composite gutters. This is going to be very quick, but I will just introduce the equation for composite gutters so that you have it, and then we will do a quick example on composite gutters tomorrow. Okay, so composite gutters. These are used very frequently in practice because they achieve that nice balance between hydraulic efficiency and safety. With a composite gutter, we have a steeper section towards the curb and a shallower section towards the street. The equation that we're going to use for composite gutters is very similar. It's just a straightforward extension of Izzard's equation. But let me draw a couple of dimensions on here for you. So just like before, we have the depth at the curb. We're going to call this D1. Okay, we have the depth at the break-in slope, which we're going to call D2. We have, so if you draw a line here from the shallow slope to the curb, you will get an intersection right here. And the distance from this intersection point to the bottom is called the depression depth, which we'll call A. So note that A is, this is the depression depth. Okay. We'll also have a couple variables for the spread. So the spread, the entire spread we'll call TW as before, but we'll also have the component of the spread that's just in the steeper slope portion, which we will call W. Okay. And we will have two different variables for these different slopes. For the shallower slope, we'll call that S sub X as before. And for the steeper slope, we'll call that S sub W. Okay. So the way that we'll essentially solve this problem is that we break up the flow into two components. We have the flow in the section that is towards the street, which we'll call QS. So let's make a dividing line here. We have the flow in the section that's towards the street, which is QS, and we have the flow in the section towards the curb, which we'll call QW. Okay. And the total discharge, Q, is equal to QW plus QS. Okay, so we can essentially just apply Izzard's equation to each individual section. And from that, we can determine the relationship between the total spread and the total discharge. Okay, so first we have that S sub X is equal to D2 divided by TW minus W. So it's the slope of this portion here. So we just take D2 divided by TW minus W, which is this length here. And from that, we get that D2 is equal to TW minus W times the shallower slope S sub X. Okay. Similarly, we can make a similar argument to find the depth D1. So D1 will be equal to the spread times the shallower slope plus the depression depth. Okay, so what we've done is essentially we've computed this length here by taking the spread times the shallower slope, and then we're just adding the depression depth to get D1. And all we have to do is we take these different depths here and we plug them back in to our expression here. So we're plugging them in for this D for each section. And I don't have enough time to go through the full derivation for that here. You can find that in the notes, but we have the following expressions for both QS and for QW. So essentially, we're just taking these D values and plugging them in to that previous expression. Okay, and so what we get is that Q sub S, so this is the portion of flow near the street. This is equal to K over N times the longitudinal slope to the 1/2 power times quantity spread TW minus W times the shallower lateral slope SX to the 8/3 power, all divided by SX. Okay. And the flow near the curb, we essentially just plug in D1 minus D2. And what we get is the following expression, K over N times the longitudinal slope to the 1/2 power divided by S sub W, so that's the steeper slope, times the following quantity. We have TW, shallower lateral slope S of X, plus the depression depth to the 8/3 power, minus quantity TW minus W times the shallower lateral slope S of X to the 8/3 power and quantity. Okay. And then the total discharge is simply equal to QW plus QS. Okay. So these are the equations for composite gutters. And we will open up our next lesson with an example on composite gutters. Okay. Okay. Thank you. And please come to office hours today if you have any questions or technical issues with ArcGIS. I'm happy to help. Have a nice weekend.